Using known Taylor series to create new power series and evaluate limits and integrals. Before we can use Taylor series, we need to know some important Taylor series. Or really, these are all Maclaurin series because they're centered at 0. So first, e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on, with the general term looking like x to the n over n factorial. And so for this guy, I try to just think about the graph of e to the x and how e to the x is always positive. So that's why all of these terms are all positive. And there's something else that we want to add here, which is the interval of convergence. So e to the x is exactly equal to this power series for all x values. So the interval of convergence is from negative infinity to infinity. Now, the sine function is exactly equal to x minus x cubed over 3 factorial plus x to the fifth over 5 factorial, and so on, with the general term looking like negative 1 to the n, because these terms alternate, and then x to the 2n plus 1 over 2n plus 1 factorial. Now, 2n plus 1 generates odd numbers, so we can see that the powers of x are odd and the factorials are odd as well. And the way I try to remember this is by knowing that the sine function is an odd function. So the sine function starts at the origin and just has this up and down behavior bouncing between +1 and -1. The other thing I tried to remember here to help me with remembering this expansion is that the sine function near the origin, it looks like the function y equals x, and so sine x starts with x, as opposed to cosine x starts with 1. So cosine x starts with 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial, and so on, with the general term looking like negative 1 to the n because the terms also alternate. But now we have x to the 2n over 2n factorial. And 2n generates even numbers. So these exponents are even and these factorials are even. But again, the cosine function starts at 1 and then it continues on from there. And so the expansion for cosine x is beginning with 1 here. And for both sine and cosine, the interval of convergence is all real numbers, negative infinity to infinity and negative infinity to infinity. For the function arctangent x, we have x minus x cubed over 3 plus x to the fifth over 5, and so on, with the general term looking like negative 1 to the n, the terms alternate, x to the 2n plus 1 over 2n plus 1. So very similar to arcsine, the only thing missing is the factorials in the denominator there. So I try to remember that arctangent x is basically the same expansion as sine x, except there's no factorials. For this one, the interval of convergence, unfortunately, is not all real numbers. So for arctangent x is exactly equal to this power series only on the interval from -1 to 1, including -1 and including 1. The expansion for natural log of the quantity 1 plus x is x minus x squared over 2 plus x cubed over 3, and so on, with the general term looking like the sum of n equals, this should say n equals 0, to infinity of -1 to the n, so there's an alternating factor, x to the n plus 1 over n plus 1. And this one also has a restricted interval of convergence. It's going to be -1, but not including -1, up to 1 and including 1. And then finally, 1 over 1 minus x, this is our geometric series. This is equal to 1 plus x squared, and so on. So the sum of n equals 0 to infinity of x to the n. Of course, this is geometric with a first term 1, and then the common ratio to get from one term to the next, we're multiplying by x. And we know that for a geometric series to converge, the absolute value of r, in this case x, has to be less than 1. So our interval of convergence here is going to be -1 to 1 with open parentheses around both. So we're not including the endpoints there because when r is equal to 1, then a geometric series would diverge. So we definitely have to have these memorized so that we could use them for building other Taylor series and then using them to evaluate limits and integrals. Before moving on to some examples, let's look at an important theorem. If the sum of n equals 0 to infinity of c sub n times x to the n, if this power series converges absolutely for the absolute value of x is less than r, so basically if the radius of convergence is r for this power series, then the sum of n equals 0 to infinity of c sub n times f of x to the n, so if we replace x with some function f of x, that converges absolutely for any continuous function f on the absolute value of f of x is less than r. So if we replace x with a continuous function f of x, then to find the radius of convergence, we need to make sure that the absolute value of f of x is less than r. In this example, we want to find a Taylor series for f of x equals 3e to the negative 2x. We'll start with the known Taylor series for e to the x. So we know that e to the x is equal to the sum of n equals 0 to infinity of x to the n over n factorial. And we'll write out a couple of terms. It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. Now, let's try to create the Taylor series for e to the negative 2x. So we want to replace the x with the continuous function negative 2x. So we'll have e to the negative 2x is equal to the sum of n equals 0 to infinity of negative 2x all raised to the n over n factorial. So what's happening in the original e to the x expansion is we're replacing each x with a negative 2x. So 1 plus negative 2x plus negative 2x squared over 2 factorial plus negative 2x quantity cubed over 3 factorial, and so on. And finally, I want to multiply this by 3. So we're just going to go ahead and multiply the left side by 3. So we're going to multiply the right side by 3 as well. So 3 e to the negative 2x is equal to 3 times the sum of n equals 0 to infinity of negative 2x raised to the n over n factorial. And I can pull this constant multiple in to the summation. So I can write the sum of n equals 0 to infinity of 3 times negative 2x to the n over n factorial. So when is this function exactly equal to this power series? So we go back to e to the x, and we remember that e to the x is exactly equal to this power series everywhere. So its radius of convergence is infinity. So the radius of convergence here is infinity, which really means that the absolute value of x is less than r, and r is infinity. When we made this substitution of a continuous function, negative 2x, what we have to do is think about whether substituting negative 2x in to x in this inequality still holds true. So here, yes, it doesn't matter that I multiplied by a negative 2 here. This is still true for any x value. So for any x I substitute in, negative 2 times that value in absolute value is still going to be less than infinity. So the radius of convergence is still infinity, and the interval of convergence is still infinity. And multiplying by a number doesn't change that. So 3e to the negative 2x is exactly equal to this power series for all real numbers. So from negative infinity to infinity, we're able to find the complete interval of convergence. It's just the same as the original interval of convergence because we replaced it with a continuous function, and when we did that, it doesn't change the set of x values that makes this true. Now let's find a Taylor series for f of x equals x squared times natural log of 1 plus x cubed. All right, so let's start with what we know from our important Taylor series. We know that the natural log of 1 plus x is equal to the sum of n equals 0 to infinity of negative 1 to the n, x to the n plus 1 over n plus 1. So now what I'm going to do is try to move on and create a Taylor series for natural log of 1 plus x cubed instead of 1 plus x. So I'm basically replacing the x with an x cubed next. So we're going to go ahead and have the natural log of 1 plus x cubed is equal to the sum of n equals 0 to infinity of negative 1 to the n, and then we have x cubed to the n plus 1 over n plus 1. So we replaced x with x cubed. That's a continuous function. And then finally, we're going to multiply everything by x squared. So the left side and the right side by x squared. So we have x squared natural log of 1 plus x cubed is equal to x squared, the sum of n equals 0 to infinity, of negative 1 to the n. And then let's see, in here, this would be x to the 3n plus 3. These exponents multiply. So we'll write x to the 3n plus 3 over n plus 1. And now I'm going to bring the x squared into the summation. So the indexing variable is n, so we can go ahead and bring in the x squared here. So we would have the sum of n equals 0 to infinity of negative 1 to the n, and then we have x squared, x to the 3n plus 3, all over n plus 1. And we can add these exponents together since they have the same base. So that's going to leave us with the sum of n equals 0 to infinity of negative 1 to the n, and then x to the 3n plus 5 over n plus 1. All right, so we have our f of x function represented by a power series, but when does this function equal this power series? What is that interval of convergence? If we remember natural log of 1 plus x, the interval of convergence there was negative 1 is less than x is less than or equal to 1. Unfortunately, we can't just say that replacing x with a continuous function gives us the exact same interval of convergence, but we can extract the radius of convergence. So here, the radius of convergence is 1 because we would know that the absolute value of x is less than 1. So the radius of convergence here is 1. So now we replaced x with x cubed. So to find the radius of convergence here, we would need to solve the absolute value of x cubed is less than 1. If we rewrite this as negative 1 is less than x cubed is less than 1, and we take the cube root of both sides, the cube root of negative 1 is negative 1, and then we'd have less than x is less than 1. So this is really just the same as the absolute value of x is less than 1. So that means that the radius of convergence is still 1, even when you replace x with x cubed. So that's great. The radius of convergence is still 1, but the interval of convergence we don't know. We have to check the endpoints. So let's go ahead and look at negative 1 and positive 1 in this series right here. So we'll do this work off to the side. If we check x equals 1, if we substitute a 1 in here, 1 to the cubed to the n plus 1 is just 1. So we have negative 1 to the n over n plus 1. This is an alternating series, so we'll check the three conditions. We have b sub n equals 1 over n plus 1 is positive when n values are greater than or equal to 0. B sub n is decreasing, and the limit as n approaches infinity of 1 over n plus 1 is 0. So this converges by the alternating series test, and 1 is included in the interval of convergence. So we'll have the interval of convergence here. So far, it does include 1. And then we'll go ahead and check x equals negative 1. If we check x equals negative 1, here we'll have negative 1 cubed, which is negative. So negative 1 to the n plus 1. And then here, negative 1 to the n and negative 1 to the n will cancel, and we'll just have negative 1 to the positive 1. So the numerator here is just going to be 1 copy of negative 1. So I have negative 1 over n plus 1. I can take the negative out. So now, to determine whether this converges or diverges, I would use a limit comparison test with 1 over n, which we know is the harmonic series that diverges. So when we do the limit as n approaches infinity of 1 over n plus 1 times n over 1, that's equal to 1, which is positive and finite. So by the limit comparison test, we know that our series diverges. And if the original diverges, then negative 1 is not in the interval of convergence. So we have negative 1 with parentheses around it. And if we actually think about substituting these x values into natural log of 1 plus x cubed, this should make sense. If I substitute in negative 1 cubed is negative 1, 1 plus negative 1 is 0, and natural log of 0 is undefined. And if I substitute in positive 1 here, then I get natural log of 2, which is definitely a value. So that does make sense in terms of representing the original function. So now this was my interval of convergence for natural log of 1 plus x cubed. Now the next question is, what about this x squared? Does that change anything? No, since x squared is a polynomial, it's not going to affect our interval of convergence. So for the final answer, the interval of convergence is still -1 not included to 1 included. Let's find a Taylor series for f of x equals 2x over 5 minus 4x squared. So what we first want to do is think about this f of x as f of x equals 2x times 1 over 5 minus 4x squared. So we know that we can find and build a geometric series when we have something that looks like a over 1 minus r. So this piece right here almost has that form, except that there's a 5 where we need there to be a 1. So what we're going to do is divide the numerator and denominator by 5. So we have 2x times 1 over 5 over 1 minus 4 over 5 x squared. So now we have that a over 1 minus r look. So we can say that 1/5 over 1 minus 4/5 x squared is equal to the sum of n equals 0 to infinity of my first term would be 1/5. So we'd have 1/5. And then my value of r is going to be 4/5 x squared to the n. So again, this value here is a, and then this value here is r. So we're building our geometric series a r to the n. So let's go ahead and clean this up a little bit. So this is going to be the sum of n equals 0 to infinity of, we have 1/5, and then we'll have, this is 4 to the n over 5 to the n times x to the 2n. So I'm raising each part in here to the n, so that here I can combine the 5 to the first and 5 to the n. So we have the sum of n equals 0 to infinity of 4 to the n over 5 to the n plus 1, x to the 2n. All right, but that was just 1/5 over 1 minus 4/5 x squared. We still have this 2x to deal with. So in other words, our function f of x is going to be 2x times this geometric power series that we created. So 4 to the n over 5 to the n plus 1, and then x to the 2n. So if we bring the 2x inside, we're going to have the sum of n equals 0 to infinity of, let's see, 2 times 4 to the n, x to the 2n plus 1. So what did I do there? I put x to the first with x to the 2n, so I add their exponents, and then over 5 to the n plus 1. Now we need to find the interval of convergence, and for a geometric series, we know that we can find the complete interval of convergence by solving absolute value of r is less than 1. But our r value is 4/5 x squared. So when is that less than 1? Well, we'll pull out the 4/5 and then multiply by the reciprocal 5/4. So absolute value of x squared is less than 5/4. And what we can actually do here is take the square root of both sides. So this is equivalent to solving the absolute value of x is less than the square root of 5 over 4, which is the square root of 5 over 2. So in other words, if the absolute value of x is less than the square root of 5 over 2, the complete interval of convergence is negative rad 5 over 2 is less than x is less than rad 5 over 2. So this is the interval of convergence on which this power series is equal to f of x, our original function. Now we want to find a Taylor series for f of x equals sine squared x. And here, I don't want you to fall for a bit of a trap, which is to think that we should rewrite sine squared x as sine x times sine x. That's not going to work. Even though we do have a power series or a Taylor series for sine x, if we write out those Taylor series, unfortunately, we cannot multiply the general terms together. And maybe if we see the expanded version, we can understand why it doesn't work to multiply these two insides together. If we write out a few terms of the expansion, how do we multiply polynomials in general? We take the first term here and we distribute it to every term over here. Well, this goes on and on forever, right? And then when we're done, although we're never going to be done, we take this and we multiply this times every single term forever. So it doesn't work to multiply summation notation together. We can add the general terms together if we're adding or subtracting summations, but there's no way that we can multiply them. With all that gone, let's focus on what we do need to do. We are going to rewrite sine squared x using a power reducing formula. So we know sine squared x is 1/2 minus 1/2 cosine of 2x. And now we can start to build a Taylor series for cosine of 2x. All right, so let's start with cosine x. We know cosine x is equal to the sum of n equals 0 to infinity of -1 to the n x to the 2n, it's going to be even powers, over 2n factorial. And we're going to write out a few of those terms, starting with 1 and so on. Now let's replace x with the continuous function 2x. So we're going to have cosine of 2x is equal to the sum of n equals 0 to infinity of -1 to the n, and then the quantity 2x to the 2n over 2n factorial. And we'll replace the x's in the expanded version with 2x's. And now we want -1/2 in front of cosine 2x. So I'm going to go ahead and multiply by a -1/2 on the left and right side. So -1/2 x, and then -1/2 the sum of n equals 0 to infinity of -1 to the n, 2x to the 2n over quantity 2n factorial. And then this -1/2, excuse me, would distribute to all of these terms here. So we'd end up having -1/2 and then plus 2x squared over 2 times 2 factorial, and then minus 2x to the 4th over 2 times 4 factorial, and so on. So distributing the -1/2 into each term here. All right, and now we wanted 1/2 minus this quantity. So let's go ahead now and put a 1/2 in front of each of these. So we have 1/2 minus 1/2 cosine 2x, that's what we're trying to build a Taylor series for, is equal to 1/2 minus 1/2 times this summation is equal to, in expanded form, 1/2 minus, and then this whole thing here, 1/2 plus, and then the remaining term. So what I want us to notice is that these first two pieces cancel. So the 1/2 that was here and then the first term 1/2 here are going to cancel out. But we have to be careful about what that means for the summation notation part. So I'm going to need a little more space. For the summation notation part, that doesn't mean I can cancel out 1/2 minus 1/2. What's canceling over here is the first term. So here, what I have to think about is how the first term is generated by substituting in the starting index of 0. So substituting in 0 into all of these n's is going to create, well, -1 to the 0 is 1, and then here anything to 0 is 1, and then 0 factorial is 1. So the first term coming out of the summation part is 1 times this 1/2, and that's how we get that -1/2. So I don't want the first term anymore. I want the second term, which is going to start at n equals 1. So our final sum is going to look like this -1/2, the sum of n equals 1 to infinity of -1 to the n, quantity 2x to the 2n over quantity 2n factorial. So the 1/2 canceled with the first term generated by n equals 0. So we still have the -1/2 in front, and we're starting at n equals 1. So we can pull this -1/2 inside. So that's going to give us the sum of n equals 1 to infinity of -1 to the n plus 1. Where's plus 1 coming from? Well, this -1, if I bring it inside, there's already n copies of -1. So -1 to the n plus 1, and then we have quantity 2x to the 2n over, we'll put the 2 in the denominator, but the quantity 2n is still in factorial. And so this is equal to 1/2 minus 1/2 cosine 2x, which is sine squared x. So this is my Taylor series representation. Ultimately, we'll come back here and put for sine squared x. But for what x values? Okay, good news for us though. Good news. We don't have a lot to do on this because this started from cosine x. The radius of convergence of cosine x is all real numbers. When we substitute in 2x, that's not going to change anything. So if I know the absolute value of x is less than infinity, the absolute value of 2x is less than infinity. And we are just multiplying by a number on the outside and then ultimately subtracting quantities. So the radius and therefore the interval of convergence will still be negative infinity to infinity. Now let's use series to evaluate the limit as x approaches 0 of 1 over sine x minus 1 over x. So here, if I were to think about substituting this indirectly, I am going to get an infinity minus infinity indeterminate case. So we would move forward with other limit strategies. And I'll be honest, what we're about to do is not the most efficient way to solve this limit, but just a way to show that you can use series to evaluate this limit. To get started though, we're going to need to write this as a single quotient. So I'm going to need common denominators here. So basically we're going to turn this into the limit as x approaches 0 of x minus sine x all over x times sine x. All right, so common denominators, right, like cross multiplying. And then what we're going to do is use these Taylor series to represent the sine function. So the more efficient way would be to do L'Hopital's rule, but we're going to use series. So we're going to go ahead and say the limit as x approaches 0 of x minus, and now I'm going to put the expansion for sine. So sine is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus, and so on, all over x times the expansion for sine x. So x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. So we can multiply here just this x times this infinite series. We're not multiplying two infinite series together, just a single x times this infinite series. And now let's simplify and see what happens. So in the numerator, this negative is going to distribute. And so I'm going to do two things at once here. If I distribute the negative to the first term, x minus x is going to cancel. So what I have is the limit as x approaches 0 of positive x cubed over 3 factorial, because this negative will distribute, and then minus x to the 5th over 5 factorial. And then, since we know the pattern, I'll put x to the 7th over 7 factorial, and so on, over, if I distribute in the x, I'll get x squared, and then minus x to the 4th over 3 factorial, plus x to the 6th over 5 factorial, and so on. So now let's think back to our limit strategies where we want to factor and cancel. So what's in common in all of these terms in the numerator and then all of these terms in the denominator? Well, in the numerator, I can factor out an x squared, and in the denominator, I can factor out an x squared, because that's what's going to cancel out. I mean, technically in the numerator, I could take out an x cubed, but I'm just going to pull out an x squared because that's what's going to cancel. So I have the limit as x approaches 0 of x squared times what we'd have left is x over 3 factorial minus x to the 3rd over 5 factorial, and so on, over x squared, and then 1 minus x squared over 3 factorial, and so on. So I just want to see what happens when those x squareds cancel. I'm able to do direct substitution. So in this previous line, to be clear, we could not do direct substitution because we'd get a bunch of zeros over a bunch of zeros. So we'd still get an indeterminate form. But after you factor and cancel something, as we know from limits, that's kind of what the goal is. Then if we try direct substitution, ideally we don't have indeterminate, and we don't because this first term right here is a 1. So the numerator is still a bunch of zeros. So we're going to have 0 minus 0 plus 0. And then in the denominator, I'm going to have 1 minus 0 plus 0. But that's not indeterminate. 0 over 1 is equal to 0. So again, not saying this is the most efficient way to evaluate this limit. That would be to combine and then apply L'Hopital's rule. But this is kind of an interesting way to get the same result. Now let's use series to evaluate an integral, the integral of x squared times natural log of 1 plus x dx. And so hopefully we can see natural log of the quantity 1 plus x is something that we have a known Taylor series for. So let's go ahead and get started here. So let's say this is the integral of x squared times, let's write the expanded version of this first. So the expanded version is x minus x squared over 2 plus x cubed over 3, and so on, dx. And then I'm also simultaneously going to do x squared times the summation of n equals 0 to infinity of negative 1 to the n, and then it's x to the n plus 1 over n plus 1 dx. So then here we can distribute the x squared. So we're going to have x cubed minus x to the 4th over 2 plus x to the 5th over 3, and so on, dx. And then here we're integrating the sum of n equals 0 to infinity of negative 1 to the n, and then we are going to have x to the, I'm going to pull this x squared in and combine by adding the exponent. So I'm adding this 2 and this n plus 1. So that's going to be x to the n plus 3 over n plus 1 dx. And now here we can integrate term by term, which is really nice. We're going to have x to the 4th over 4 minus x to the 5th over 2 times 5, so that's 10, plus x to the 6th over 6 times 3, which is 18, and so on. But we know that indefinite integrals need a plus c, and we don't want to put dot 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 plus c. So we're going to put our plus c at the beginning. So we're going to say c plus this quantity here. And then now over here, I want to go ahead and integrate with respect to x. So we're performing the antiderivative part on the x to the n plus 3. So we're going to have the sum of n equals 0 to infinity of negative 1 to the n, x to the n plus 4. So remember, we add a number, add 1, and then divide by that new power. So there's already an n plus 1 down there. So there's going to be an n plus 4 down there. And then we're going to need a plus c. So I'm going to put that plus c in the front. Here we want to use the first 4 terms of the Maclaurin series to find the definite integral from 0 to 1 of sine of x squared dx. Now here, because we're going to be terminating our Maclaurin series with the first 4 terms only, this is going to give us an approximation for this definite integral, not an exact value. But we do not have the tools to integrate sine of x squared. So this is going to be a really good way to at least approximate this value because we don't have any integration techniques for finding the antiderivative of sine of x squared. But we can, as we know, rewrite sine of x squared using the Maclaurin series for sine of x, replacing each x with an x squared. Now, thankfully, the interval of convergence for sine is all real numbers, so when we replace it with x squared, it's still going to be all real numbers. So for this definite integral to be defined on 0 to 1, that's going to be fine. We can still use this Maclaurin series without any issues with the interval of convergence. So I'm going to go ahead and do that. I'm going to replace x with x squared. So it would normally be x and then minus x cubed over 3 factorial. So we're going to have minus x squared cubed over 3 factorial plus x squared to the 5th over 5 factorial minus x squared to the 7th over 7 factorial. So we're going to use just the first 4 terms. So we replaced each x with x squared on the sine x expansion. And now we're going to integrate term by term here. So let's see. Let's simplify the exponents first. So we have x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial dx. So now let's take the antiderivative of each term, x cubed over 3 minus x to the 7th over 7 times 3 factorial. I am not even going to bother multiplying the denominators. Plus x to the 11th over 11 times 5 factorial minus x to the 15th over 15 times 7 factorial, evaluated from 0 to 1. Good news here, we can just substitute 1 into each x because substituting in 0 will be minus 0. So we can say that this is just 1 over 3 minus 1 over 7 times 3 factorial plus 1 over 11 times 5 factorial minus 1 over 15 times 7 factorial, which if we substitute it into a calculator to approximate, it's about it's about 0.31027. So that is using a Maclaurin series to find an approximation of a definite integral. Because we didn't actually use the entire power series, we only used the first 4 terms. But how could we use the entire power series? How can we substitute these values into infinitely many terms? We can't. So this is going to be good enough. And it turns out there's not that much error involved in doing this. So it's kind of nice and kind of quick.